1324, presenting our final project for MAE 3340, Instrumentation and Measurements. We tested various 3D printed infill patterns for their stress-strain data for the benefit of hobbyists and others seeking the best infill choice for compression. Within the 3 infills we proved the best results. The octagram infill had a yield strength of 29.55 megapascals plus or minus 3.20 megapascals. We hypothesized that the infill pattern would significantly affect the compressive yield strength of the cylindrical samples, assuming constant geometry and dimensions otherwise. Given our understanding, we hypothesized that of the tested infill patterns, gyroid infill was predicted to maintain the highest yield strength. Given the data for PET-G that didn't have an uncertainty bound, we weren't able to do chi-squared testing, and therefore no numerical testing hypothesis could be done.
In order to test this project, we used a compressive tester, and we tested the specimens between 2 flat horizontal plates. The specimens were 3D printed with a diameter of 1/2 inch and a height of 1 inch using a Prusso Core 1 printer. We tested 5 different infills on 6 samples of each, and we were able to receive stress, strains, and forces from the tester and the computer. Some alternative specimens used was a dog bone specimen and a large diameter puck specimen. We started with the dog bone specimen. This specimen failed by buckling instead of compression, and then when moving to the large diameter specimen, it worked. However, it took too much time to print and test and too much materials for each specimen. We ended up settling on a small diameter specimen to save on time and materials. Additionally, alternative grips were used as well, starting with clamp grips to clamp down on the specimens. This grip was difficult to clamp up perfectly onto each specimen without putting the specimen to failure. We then tried to use a flat plate and a hammer grip. However, it was difficult to get a perfect placement of each sample underneath the hammer, so we settled on 2 flat plate specimens. Additionally, when working with these tests, we used safety glasses and avoided having our fingers in pinch points in order for safety. Assumptions made in this test were that the 2 flat plates distributed an even load, and the loading was in perfectly axial force, no bending force. We also assumed that the material properties were uniform and there was a constant and solid cross-sectional area. These assumptions enabled us to perform the test and receive the data and then follow the equations.
The primary governing equation for this test is the standard stress equation of force over an area. The equation seen here is simplified, and the uncertainties for each instrument used are listed.
Our previously stated hypothesis is that the strength of the material for a certain infill and percentage is a portion of the theoretical strength of the solid material. The factor, C infill, can be solved as the experimental strength divided by the theoretical strength. The theoretical model will be compared to the experimental compressive strength at 100% infill.
This slide presents all data collected per infill type. The bottom right is our control graph for 100% infill, and each one of these graphs has a different scaling in stress and strain. Final numerical values are listed here in Table 1 from lowest strength to highest, with each uncertainty listed in coordination. All of these are at 95% accuracy using error propagation and the student's T statistical test.
The left column here shows that the factors of each infill is compared to the solid test. The right column shows the factors compared to the theoretical model. As you can see, the theoretical model pretty accurately predicted the experimental data with reasonable accuracy. Small differences can be attributed to small integrity issues from the 3D printing process.
95% confidence, we cannot accept our initial hypothesis of the strongest yield strength resulting from the gyroid infill. Instead, the 3D honeycomb, and octagram spiral infills were statistically similar as the strongest results. They fall within 46.37% of the strength of the solid infill control body. If provided an opportunity for improvements, we would expand our sample size as well as testing to include additional types of tests, including multi-axial, tensile, torsional, and shear stresses for a greater completeness of data.
We are now to the appendixes. The first appendix is the Design Decisions appendix. The first component in here is the specimen. The first option for the specimen is the chosen specimen of the smaller diameter. It works through optimizing geometry with good compression. Its strength is that it is efficient in both time and material cost, and it provides good data. With weaknesses of 3D printing error in the circles, as 3D printing error is an X and Y coordinate plane, and we had to switch it to a circle. It is chosen because it meets all of our needs and is efficient. The second specimen was the large diameter specimen, which is similar to the small diameter specimen, with the difference of increased time in both printing and testing, while using more material, increasing the cost. The final specimen was the dog bone specimen. This specimen was not chosen because when testing in compression, it failed in buckling, not being able to provide good data. The second component we used was the compression apparatus. The first option that we used was with the dog bone specimen, which was the clamping grips. The clamps had strengths because they were very exact in testing and they had no movement or frictional error. However, it was difficult to get into a perfect placement on the grip for this cylindrical specimen and getting exact placements. The second apparatus we used was the hammer top. For this, it was efficient in compression and gave exact forces, however, was once again difficult to get an exact placement. Because of this, we rejected this apparatus. The final apparatus which we accepted was the two flat plates apparatus. We chose this because the plates distributed the loads evenly, enabling us to get good data without having to get the specimens in the exact perfect positions. There were some weaknesses with imperfect distributions. However, we were able to get good enough data for our tests through this apparatus.
Appendix on uncertainty analysis. Here we can see the bias and precision mathematics. Bias is a result of the build quality and calibration of the machine and tooling that we used. Here it is the force of the load cell sensor and the accuracy of the X and Y axes of the Prusa 3D printer. The precision error analysis is to handle statistical variations in the specimen quality.